This will continue the lectures on neutrino physics, introductory lectures that the first one started today. Okay, right, so for questions, please ask in the chat or use a raised hand to be unmuted. No Q&A, please. That's an announcement from Ethan. I'm just reading it in real life. So, right, so questions are important, and you know, it's good for me to get like some feedback from my audience. I'm not seeing your faces, so I don't know if you guys are, you know, if you went to sleep or if you're watering your garden. However, I realize that, you know, we can't handle questions from 80 people during the talk. So what I want to say is that we're going to use the coffee rooms for their intended purpose, which is to answer questions and further discussions. So questions and discussion. Coffee room. And I'm told that 3 are available. All 3 today are available. So let me just pick the Electron coffee room today, just to make it certain. So come, and I will try to see my best what I can do to answer your questions. Okay, all right. Then I think the announcement was already made. On Thursday, we had a little permutation. So there was an oscillation between lectures. So my lecture is going to be the 3rd of the day. Okay, very good. So what did we do in lecture 1? Lecture 1, we did basically an overview of the subject using the historical framework to introduce many concepts. So we know that neutrinos are chiral. Which is to say that if you take the neutrino spin and you measure it, it turns out to be always anti-parallel to its momentum. And for antineutrinos, if you perform the same measurement, then you will discover that it points in the same direction. Obviously, you know, this means that neutrinos behave as massless fermions. And indeed, you know, if you think about all experiments that we have done in terms of their creation and detection, neutrinos are acting as massless chiral fermions. The way you see the mass is through oscillations, which is a very delicate and subtle interference measurement. And mostly when you don't do these experiments, you don't know that neutrinos have a mass. So that we learned. We also learned that neutrinos interact only weakly. Which is to say that, you know, W and Z are involved, but no photons or gluons. And this creates some unique properties in the lab and in astrophysics and in cosmological settings. Okay. And then, of course, neutrinos oscillate. Which we argued wasn't known for decades of neutrino experiments. And then in the last 20 years, has firmly entered textbooks. So they have, as a result, it means they're not massless. They have non-zero masses, which are, however, tiny. And then the flavor and mass eigenstates for these neutrinos are distinct. Okay. And we'll talk about today mostly about oscillations, since we actually have to talk about how and what happens, and we'll see how we get there. But what we have reviewed so far already, that oscillations happen in solar neutrinos. Also atmospheric, also reactor antineutrinos, and neutrinos made in laboratory beams. All of them have been shown to oscillate in ways that are irrefutable. And so then we have to understand how to explore the current wealth of data. Now, a short digression that came up yesterday, and some people asked, the question was, you said that the physics Nobel for neutrino oscillations was given in 2015. What about Ray Davis? I heard that Ray Davis also got a Nobel Prize. So that is true, he did. And I think I'm gonna quickly show this to you guys. Indeed, there was a prize that was given in 2002. And the important historical note here that it was certainly given to him for doing the Homestake experiment, and to Koshiba it was given for doing the Kamiokande, the original Kamiokande experiment. However, it was mainly or exclusively actually for the discovery of astrophysical sources of neutrinos. So not for oscillations, even though when it was given in the fall of 2002, we already had SNO neutral current data. And so it was getting, very quickly, it was getting plenty evident that not only they measured neutrinos from the source, which was known in the case of Davis since the late 60s, but also that the measurements were correct and were in fact sign of new physics. But, there is this, of course, the whole long story about who got the prizes and for what and who didn't. So, for example, John Bacall, who was a partner of Davis, the theorist who computed the solar model and who led the theoretical developments of the subject for 2 to 3 decades, did not receive the prize, which, for me personally is difficult to justify. Then, of course, we know that there was a story of Fermi, who got the prize in 1938, I believe. However, for Fermi to be completely, explicit in that case, he got the prize for experiments involving neutrons. So Fermi, in the second half of 1930s, discovered, well, for himself, that he could bombard. Sorry, something happened. Can you guys hear me?
Yes, we can hear you.
Okay, sorry about this. My computer is freezing. Right. So to make the long story short, Fermi was doing experiments with neutrons. Neutron was just discovered in 1932. Neutrons were scattered on heavy things like uranium, and he thought he was making new transuranic elements, and those earned him the prize. Their slides have disappeared. Good point. So how about my Zoom thinks that it's still sharing.
Yeah, we don't see any screen share.
Yeah,
right?
no, I don't see it on my computer either. So I'm restarting. Do you see it now?
Yes.
Yeah,
Yes.
sorry about this. Right. So anyway, about different Nobel Prizes that we started talking about yesterday, Fermi thought that he was creating new elements by bombarding things like uranium with neutrons. Turned out in retrospect that he was seeing fission products. But anyway, the Nobel Committee decided to award that prize to them for this work. And of course, Einstein didn't get his Nobel Prize for relativity, but for the photoelectric effect. There's nothing wrong with the photoelectric effect, but it's kind of startling that the relativity thing didn't get any prize, and so on. So one can go into the history of these subjects. What I do want to turn back to is that, yes, there was a Nobel Prize given for Ray Davis, but as of 2002, even though the data was mounting, it was still given just for the detection of astrophysical neutrinos. In the case of Koshiba, it was for neutrinos from the supernova that were seen by Kamiokande. Sorry, yes, by Kamiokande. Not for discovery of oscillations. Okay, so that's that. Now, today we're going to do some statements about oscillations. And as I said, the idea is that there is a misalignment of flavor and mass eigenstates. So what that means is most readily understood if you go back and you think about the quark sector. So in the quark sector, we have up-down quarks, up, strange, and top. Let's just for now think about the first two. And then you have D, and then you have strange. And when the up quark emits a W and creates a state in the down sector, turns out that it does not create the state that's equal to the D quark. What it creates is a state that is a superposition of D and S. And this was first realized by Cabibbo. And this angle is known as the Cabibbo angle. So very simply, the state U does not couple to that, to the D, but to something called D prime. And then, of course, when you consider that there is the orthogonal linear combination, then charm couples to that orthogonal combination. So the charm quark, when it emits a W, turns into minus D sine Cabibbo plus strange cosine Cabibbo. And so that when you measure these processes carefully, you can actually see that, for example, neutron decay knows that U and D misaligned at some level. Now, if in retrospect, it's actually rather surprising that the families are ordered by mass. So when we talk about U and S and D and Z, what we actually mean are states of a given mass, which are eigenstates of the Hamiltonian that's created once you take the Higgs coupling terms and you put the Higgs to its vacuum expectation value. So there is some physics that creates those states, But that physics seems to not follow what the weak interactions do. And at least it's surprising that there is some connection at all, right? So for example, if you look at the third generation, there are states top and bottom, which are mass eigenstates. And it's rather surprising that top, when it emits a W, goes into a state that's almost exclusively bottom. There is physically no reason for it. If these states D, S, and B didn't have any mass, then you would just consider whatever linear combinations you could think about, and then the linear combinations that coupled to certain quarks would just be labeled like a down quark of U type and a down quark of C type and a down quark of top type. And that's actually what was happening in neutrino physics for many years. If you look at the old PEG listings, for example, you'll discover that for neutrinos, there was an interesting disclaimer. And the disclaimer was that all particles that are listed, what do we call a particle? What we call a mass eigenstate, a state with a given mass. So all particles that were listed there were eigenstates of mass, except it said for neutrinos, they are eigenstates of flavor, which is to say partners of the charged leptons under weak interactions. Okay, so now there is, of course, a matrix that connects these flavor states. And the states of certain masses that we measure. And that matrix, traditionally has this notation and so forth. So you get the picture. So this one is VTD, and this one is VTB, and so forth. So this is the CKM matrix for Vigo, Kobayashi, Maskawa. Kobayashi and Maskawa took it to 3 generations, which had important implications for CP violation. But anyway, so at least in the quark sector, there is some semblance of order. Lighter masses in the up sector line up to preferentially line up to lighter masses in the down sector. And the same was expected from neutrinos. Long story short, of course, you know that it turned out that the neutrino sector does not look at all like the quark sector. And so that provides major input in the way we think about the origin of masses and flavor. So now what we have for neutrinos is we have 3 mass eigenstates. They are labeled by names mu1, mu2, and mu3. And we've measured the squared splitting of these masses, and we measured the squared splitting of these masses. We don't know the order of the states, so that, for example, you could have states like this. And at this point, we're not sure what the order of the states is, and to understand that requires a more precise studies. Okay, so we're not sure yet. This one is called normal hierarchy, normal mass hierarchy. And this one is called inverted. And sometimes hierarchy is called ordering. Okay. So there is a matrix that connects the flavor states that are defined by charge current weak interactions. And there is a matrix called PMNS matrix that connects the two bases. And PMNS stands for Pontecorvo. Maki. Nakagawa Sakata. Okay, so that's the basic fact of life, that there are certain physical processes that we don't fully understand that make neutrinos massive. And these physical processes don't seem to know very much or care about the physical processes that define the basis of weak interactions. And the phenomenon of the oscillations comes from this. So let's, to simplify things, let's do two flavors first. Two flavor case first. In this case, we'll just pretend that we have nu e and nu mu. There is a small matrix. Let's see. Sorry, I'm going to take a look at the chat. Delta 1,3 is biggest, or delta 2,3 is biggest. So for now, we're just talking about notations. There are two splittings. You can call them whatever we like. Most of the time, I will refer to this small splitting as delta m squared solar. It's sometimes referred to as delta m squared 1, 2. And then there is the big splitting, which is an atmospheric splitting, delta m squared atmospheric, because it's the leading effect in atmospheric neutrino oscillations. And you know, then when you start doing very precise measurements, which is the goal of the next generation of experiments, it actually matters what ordering you have and how you define these things, whether delta m squared atmospheric is between the 2 and 3 state, or it's between 1 and 3 states. The current level of precision, actually, it doesn't matter, because we're not sensitive to that small splitting when we're looking at the big splitting. But okay, let's just continue. So we have nu1, nu2 connected to nu e, nu mu. And so let's count our parameters. So this matrix, in this case, is a 2 by 2 unitary matrix. So it's subject to this constraint. So you start with 8 real parameters from a 2 by 2 complex matrix. And then when you impose the unitarity constraint, you end up with 4 real parameters. And then you can think about the phases of your base states. So you can absorb phases of the matrix into the phases of mass eigenstates. It's our choice. And then we also have the phase of one of the other states, say nu mu. And the last phase we do not have available, because if you consider the overall phase that acts on the mass basis, then that commutes with V. So you do not have a choice of 4 phases, you just have 3 phases in the total phasor definition. So what that means is that you have 4 parameters minus 3, and at the end you just have 1 real parameter. And that real parameter is the mixing angle between the states. So the matrix simply becomes cosine sine minus sine cosine. Okay. So consider what happens in the sun. So let's say I have two protons as my first reactions. These guys get together and they form a deuterium, which is a p-n state. And of course, you know what that means is that you create a positron to conserve the charge, and then you create an electron neutrino. And then this electron neutrino, which is created as a flavor eigenstate, then is decomposed into the sum of mass eigenstates. Now, again, I emphasize that the mass eigenstates are the physical particles. And so normally in physics, we try to create elegant names for new particles that we discover. So we have charm, and then we have strange, and all these other elegant names, you know, even things that have not been seen have beautiful names like dark photons and so forth. In neutrinos, we have terrible nomenclature. We discovered that there are 3 particles that we didn't know existed before, and we call them nu1, nu2, and nu3. Marketing is not our strongest suit, but you know, we have really interesting physics phenomena that happen with these particles. So
there's some questions in the chat if you want to look at them.
Yeah, let me take a look at that. Yeah. Could you please repeat the absorption of phases argument? So when I just introduced states nu1 and nu2, and the definition of the phase, I mean, how I define that state is up to me entirely. What I will care about in the future are physical differences of the phases that accumulate as a result of the travel of wave packets. But for now, as a starting point, I can create a state and define it to be anything I want. This will also will come up a bit later in various representations. Hopefully it will be made clear. But this absorption of phases, the argument is completely generic. And it's the same story that you do in the quark sector. So actually, if we'd like, let's just do a general counting. So I did a 2-flavor example here, but let's just skip a bit and let's do a general counting. So we have, if we have a matrix U, and it has 2n squared real parameters, and this matrix is unitary. This unitarity provides n squared constraints, which means that I have 2n squared minus n squared parameters left. And now I'm doing the same exercise that my mass basis states can be defined with arbitrary phases, only the difference of phases that accumulate then matter. And my flavor states also can be defined with phases -1. So in -1, because the overall phase from mass eigenstates commutes with the matrix V. So then I have phase redefinitions that give me 2n minus 1 constraints. Okay, so then what I have left is n squared minus 2n plus 1, which is n minus 1 squared, independent parameters after I redefine this. And that's my number of physical parameters. So in the case when n equals 2, I had 2 flavors. So n equals 2, I had only one parameter, and that's the mixing angle. N equals 3 is going to give me 4 parameters. And then for n equals 4 and on, it really, you know, things get out of hand very quickly. But okay, what I would like to do now is I have these parameters, and I would like to identify them a bit better. So what I have when I do rotations of the type that I was doing before is I do a rotation, which is a real transformation of the type cosine sine minus sine cosine, the other things being ones, and these things are zero. And I have a bunch of these rotations corresponding to each of the item here and actually all the entries in this triangle. So that's going to be n minus 1 over 2 different rotation angles that I can define. And now what I'm left with n minus 1 squared minus the number of rotation angles that I defined. And as you can see, this is equal to n minus 1, n minus 2 squared. So this is the number of complex phases that are present in my matrix that I have not been able to absorb into my initial or final states, or constrained by the arguments of unitarity. And these are contributing to real physical phenomena, in particular CP violation. As you can see, for n equals 3, there exists a 1 phase according to this counting that we just did. We already know this. If you go back and you look at your CKM matrix, the CKM matrix has one such phase. It's responsible for what we talked about yesterday, that, you know, K long decays to 2 pions about 1 in 300 times. So CP violation and the quark sector is accounted by that phase. And now the hunt is for neutrinos. Okay, hunt is to see if in the neutrino sector there is this phase that is accounting for differences in oscillation probabilities between neutrinos and antineutrinos. We'll come to that. Now, so the question again online is why n minus 1? So what is the meaning of, you know, this thing that I always subtract this one phase? Well, so imagine I have my CKM matrix and I have my base states, nu1, nu2, and I multiply each of them by e to the I phi, e to the I phi, right? This is the same as multiplying everything by the identity matrix, e to the I phi times the identity. So I'm just being very explicit here, which commutes with this, which means I can take it to the other side. And then if I wanted to define the overall phase on the flavor states, that has already been accounted for. So that's why. But again, here I'm not teaching something that's specific to neutrino physics. It's the standard argument and the standard model that applies to the CKM matrix. Okay, what is relevant for PMNS matrix is the parametrization. So the PMNS matrix is traditionally parameterized in terms of 3 angles, and these are defined as follows. So you do a rotation between 2 and 3 states, right? So I told you that there are real rotations. So the first convention is to do this rotation between 2 and 3. Then there is a rotation between 1 and 3. So cosine and minus sine 1, 3, and then cosine here 0, 0, sine theta 1, 3, and I'm going to leave some space here. And then the third matrix is cosine 1, 2, sine 1, 2, minus sine 1, 2, cosine 1, 2, 1, 0, 0. So here we have 3 rotation angles. And as you can see, the outer matrices just have real rotation angles, because those phases you could pull out and absorb either into mass eigenstates or into flavor eigenstates. The middle matrix has a phase which is stuck. It's there. And this is the famous delta CP phase. Delta CP that we are hunting for, right? So you can see that delta CP is the phase of the sine of theta 1,3, right? So the angle theta 1,3, the sine of this angle is complex, and its phase is the physical delta CP phase. So we did the counting, and now we introduced the standard parameterization, and that's the parameterization that is used in this subject. So I'm happy to discuss this more offline and coffee or whatever, contact me. For now, I'm just gonna go back to my oscillation problems. So I'm going back to oscillations, and I'm doing two flavor oscillations for now. So what I found before is that I created a flavor state, and I need to project this state onto the mass basis, because the evolution in the mass basis is going to be especially simple. So that's my rationale for doing this. And of course, you know, oh yes, right. So to simplify, not only it's two flavors, so it's a two flavor case, but also this is happening in vacuum. Vacuum means that the presence of matter does not change the oscillation Hamiltonian. It's true in some cases and will be seen to be not true in other cases, in particular in the sun. You have to take matter into account. Also in the long baseline experiments. But for now, I'm just doing vacuum. So I have an oscillation Hamiltonian that's relatively simple. And in this case, if I have a new one state evolves by a phase that has to do with its mass or its mass splitting from the other state. So I'm going to say that there is a cosine here. So this evolves as a function of time. This state evolves as a function of time into e to the minus I delta t, where delta is the energy, delta 1 is the energy of the first state, and sine squared e to the minus delta 2 u2. So this was the point of decomposing the flavor state into the mass state, is because on the mass basis, the evolution is that things are simply multiplied by the energy of that state and by the exponential e to the minus I delta t. Okay, and that's it. So then you have to reassemble this state later, and that will give you oscillations. So this is a very simple point, but it's an important point. So if there are questions, now is a good time to ask them. By the way, what is delta? Well, if you consider that your energy is, for a relativistic particle, is its mass times p squared, and you are expanding this in the ultra-relativistic limit, then we have p plus m squared over 2p plus dot dot dot. And to keep the leading terms, we can choose E for p here, and we can choose E for p here. So this is the neutrino energy. And then you can see that delta is delta m squared over 2e nu. There are some important subtleties here, because here I assume that the two neutrino states propagate at the same momentum. Like you can make an alternative statement. If they have propagate with the same energy or with the same velocity, you get the same answer to the same order. Actually, if you are very pedantic, it's neither fixed momentum or fixed energy. But these are subtleties that I don't want to go into just yet. So the important point is that the difference of energies of this state, so So this is delta 1, and then delta, which is going to be defined as the difference of delta 2 minus delta 1, is defined as m2 squared minus m1 squared divided by 2e nu. And in turn, this is equal to delta m divided by 2e. Okay, that's delta. For the purpose of future, for convenience, I'm actually going to call this 2 delta. Turns out to be convenient. The equations have fewer factors of 2, but never mind. Right now, these are just definitions. So why don't we just keep neutrinos on the mass basis always, like we keep the quarks? That's a very good question. The issue is that you can think about what you do in neutrino experiments and what it is that happens when you measure a neutrino. When you create a detection phenomenon, for example, a neutrino arrives from the sun and then it strikes an electron in the Super-Kamiokande detector, and it creates an electron, an outgoing electron. This measurement is a measurement of the neutrino flavor. So all the production and detection experiments that we do are only concerned about the flavor of the neutrino state. I mean, in fact, it's very hard to figure out, that neutrinos had a mass. It took a long time. So because of this, experimentally, we have overwhelming need to think on the flavor basis. We create a state from a process of weak interactions that has a certain flavor, and we measure it in a flavor-specific way. Then why is the same not true for quarks? Well, very good, because you have a stationary quark and or mesons that you can weigh them, you can measure their mass. If you have a pion, quarks have charge. Well, yeah, that's true, but that's not the point. The point is, again, and if you forget about masses of the quarks, then the quarks of the bottom variety, so down, strange, and bottom, they actually have identical interactions. In terms of gauge interactions, they have exactly the same properties. So if you did not have masses for these particles, you could indeed forget that what you call U and what you call D and so forth, and just consider states which are connected by weak interactions. But what you call a proton is a state that involves UUD, and these UU and D are states of given masses. Okay. And the same is true for K mesons and so forth. These are states of given masses. So you have properties of given masses. Neutrinos are very special in this way, is that in every setup you are worried about, in detection and creation, you are worried about the flavor. And then when you create a certain flavor and they propagate according to their mass eigenstates, you measure the system some distance away and you discover the flavor magically changed. Also, the electron produced in neutrino interactions processes would be in the flavor basis, right? Yes, right. So you create, in the case of, for example, solar neutrino, you're just not able to create a muon because the solar neutrinos have energies of a few MeV, and muon is over 100 MeV in mass. So you're not able to create a muon in the SNO or Super-Kamiokande detector. And what that means is that your detection process is very clearly favoring electrons. So it measures in terms of the underlying physics. Yes, you have mass eigenstates arriving to you from the sun, and then your detection process measures the electron component of this eigenstate. Okay, very good. So now we have to do some oscillation studies. So we create an electron neutrino, and we would like to see what's the probability of it going to muon. I'm doing a 2-flavor formula, but I can actually just do it in full generality. If I'm doing vacuum oscillations, the argument is the same. It already should be obvious what it is. I'm going to do it in steps. Okay, so the first step is that I will take the state that I originally created as a neutrino flavor I, or alpha, and I'm going to evolve it. So is it clear what I did here? This should be fairly clear, but let me know because this is an important point. So I create a state of flavor alpha in the beginning. I change my basis to the mass basis. So I project it onto mass basis, which are new J's. And then once I have my new J's, then I have a sum. This is summed over J. And this is my evolution of the state as a function of time. That's it. So now then, when I would like to measure this again, I measure this, and I measure it on the flavor basis. So I use the state, that's beta, which may or may not be the same as alpha. And then here we go, new beta, new J, e to the I delta J T. T is, by the way, completely replaceable by L, since these are ultra-relativistic particles. New J, new alpha, right? That's what I have. That's my amplitude for transition. And then the probability, new alpha to new beta at time t is going to be the absolute value squared of this quantity. Yeah, again, I mean, the repeated indices are summed over, but let me just write this explicitly here, so that there is no ambiguity. J, and there is a sum over J, and an absolute value here. So that's it. That's the general formula in terms of the CKM matrix entries. It goes like this. If I do, again, my 2-flavor case in vacuum. Oh, that's not good. I lost my broadcast again. Can you hear me?
We can hear you, yeah.
Yeah, I am.
We can see you too.
Yeah, I'm restarting. Sorry about this.
And in the meantime, there's one question I think you left out.
I left out. Let me
Yes,
take a
so it
look
was
here.
asked again.
Why? Let's see. Is there new E or new 2 on the right-hand side? Well, if I knew which right-hand side, I would.
It's about why you seem to use the Schrodinger equation instead of the Dirac equation.
Oh.
It's not my question.
Yeah. May I ask why we apply the Schrodinger equation rather than the Dirac equation, or why is it only unitary evolution? Yeah, that's very good. Let's make a note and come back to this. Indeed, there is an issue of this is an ultra-relativistic system. You want one way of thinking about this that will make it very simple is to go to the rest frame of this now massive particle. And you will see that in this rest frame, you get you just get the difference of phases. That rest frame is almost well defined. It's not perfectly defined because the states have slightly different masses. So in the rest frame, you have actually two wave packets that are slowly shifting relative to each other. Well, let me not worry about this. I just go to the rest frame. I have a particle that is in the superposition of two states. This is the case of simple Schrodinger evolution. Then once you derive it in the rest frame, you can boost it and you will obtain the same delta m squared over 2e in the frame of the laboratory. The line above the delta in the expression for here, I'm sorry, yeah, that is a 2, but I can see how you could think it's an e. So let me try to be neat here. Maybe I can tell my pencil to be thinner. Let's see if that does the trick. So in the 2 flavor case, yeah, it's 2 here because I was trying to change things to the mass basis, where in the mass basis, I just, I mean, the evolution is trivial, just multiplied by the phases as a function of time. So then for the 2 flavor case, you can substitute things and you're going to do, let's say you have started with mu e and you want to go to the flavor mu, and if you do the substitution, then you get cosine sine minus sine cosine, and then you have e to the I delta t squared, where, you know, each of these terms had a phase, but since we're taking absolute values, it can take one out. So only the physical phase difference appears. That's the phase that appears in the second term. So that's what I have. Now you just do some simplification where you get cosine squared sine squared here. And then here you get absolute value of 1 minus e to the I delta t squared. And then cosine and sine stay. But here I get the first term absolute value squared plus the second term absolute value squared and minus 2 real part of this guy, of the product. And that will be cosine sine 2, 1 minus cosine delta t. And that will be, I take 1 minus cosine and I rewrite it one more time, I get sine squared delta t over 2. And finally, this takes the familiar form, delta t over 2. That's it. That's the oscillation formula that is found in all, you know, textbooks. 4 times t. Okay, let me just finish this and then I'm going to see the question. So this is the probability of flavor change. You can see at time t of 0, you start with no other flavor. As time progresses, then you oscillate. So the probability, appearance probability, increases, goes to the maximum value that's determined by this term. The mixing angle tells you the maximal value of the probability, and then oscillates back and forth. Okay, now if I instead wanted to do a probability that the electron neutrino remains the electron neutrino, then what I do is I take the same thing and do 1 minus that. So that's going to tell me the Serrayol probability in this case. And then finally, in terms of physical parameters, in terms of quantities that people know and love, or in this case, in terms of the baseline of the oscillation L, you get this canonical result where it's sine squared it's delta M squared in EV squared. The EV squared. Okay, let me get myself more space, since this is a nice formula and is seen very often. Delta M squared in EV squared, energy in GeV, distance in kilometers, and the factor here is 1.27 in these units. So you can apply this to several settings, and you can very quickly get some useful results. For example, if you have atmospheric neutrino oscillations, the energy is ranged broadly, but let's take a 1 GeV or GeV to be the relevant scale. In this case, delta M squared of 10 to the minus 3 is going to give you the oscillation length of 1,000 kilometers. So that's a good scale to probe on the size of the Earth. So atmospheric neutrinos, if V of order GeV and delta M squared of order 10 to the minus 3 EV squared, then L is of order 1,000 kilometers. So the Earth is your friend in this case. Then for the same atmospheric splitting, but with reactor neutrinos, so if I have reactor antineutrino, then I have energies of order MeV, and then the same oscillation frequency that guides the atmospheric scale is going to give me a baseline of about 1 kilometer. So these are relevant things for experiments like Diabase, Reno, and Double Show. This is how the third angle θ13 was measured, by placing detectors about 1 kilometer away from the reactors. Then if you would like to use the same scale, the same energy of reactors, but you would like to probe delta M squared 1, 2. So this is delta M 2, 3 or atmospheric, and 1, 2 is of order 10 to the minus 4, 10 to the minus 5. Let's say 10 to the minus 4 EV squared. Then you get L of order 10, 100 kilometers. And that turns out to be a good distance scale on the size of Japan. So this is what the Camland experiment had accomplished. It saw oscillations with an average baseline of about 150 kilometers. I say average because, of course, they have a bunch of reactors, and it's not, obvious. Well, you have to be careful. You get a superposition of these fluxes. Okay, so much for the distance scales. Now I want to switch back to here, and let's just together admire this graph. This is the result from back in 2012. Well, actually, this paper is 2015. 2012 is when Diabase first reported its results, and 2015 is the year when they had very, very precise measurements. You can look at the blue histogram, which is here the unoscillated spectrum, expected unoscillated spectrum. Oh, there we go. So blue is the unoscillated spectrum, and red is what is actually observed. And you can definitely see that neutrinos have disappeared. And then if you take this data and you rebin it as a function of effective L over the neutrino energy, you get this figure on the right, and you just get this beautiful sine wave. So that's you know, exactly what we just derived. So this is a quantum phenomenon which has a very classic oscillation pattern. Let's see. Does this make sense? I'm gonna have to, now I'm gonna go back to the chat and see what's happening there. The time is arrival in the detectors, but the neutrinos have masses. Doesn't that mean that they would arrive at different times since they have slightly different speeds? You know, that's actually, that's an excellent question. And this detector, this detection business and the whole oscillation business is subject to all the usual quantum mechanics challenges, if you like. So the time of emission of the neutrino has some duration. And that is essential, that there is an emission of the neutrino has some duration. You detect the neutrino at some point, but then the emission process has some duration and you get an interference of wave packets corresponding to nu1 and wave packets corresponding to nu2 because they were emitted at slightly different times. When you wait for long enough times, or in the case of, you know, real life scenarios, let's think about supernova neutrinos, which travel, you know, say 8 kiloparsec. Then by this time, the wave packets corresponding to different mass eigenstates have definitely separated by the time they reach the Earth. So vacuum oscillations for supernova neutrinos, the part that occurs between us and the supernova, is extremely simple. It's just an incoherent sum of mass eigenstates. In the case of like reactors, the point is that over 200 kilometers, the wave packets have not yet separated. And so you are observing this interference phenomenon. You can actually, you know, it's a good topic to ponder. So I'm going to get into trouble for getting another digression, but I think these are very good questions. So oscillations is like it's a true quantum mechanics phenomenon. And its quantumness can lead to all the usual paradoxes. So for example, you know, you create a neutrino. So let's say I create neutrinos by taking pions and decaying them. And this is how neutrinos are created at Fermilab in their beam experiments. So you have a decay pipe, you send pions here, a pion decays to a muon, and in this case, it's a muon, so it has to be an antineutrino. So you have an antineutrino. The antineutrino is collimated, but the point is, like, it's a two-state process. And so the question is, if I had measured the energy and momentum of the initial pion extremely well, and if I had measured the energy and momentum of the final muon extremely well, at least in principle, then I know exactly the energy and momentum of mu, and therefore I can, you know, figure out its mass. So the mass of the neutrino is going to be the neutrino energy measured extremely well, and the neutrino momentum measured extremely well. And so then in principle, if I do this extremely well, then don't I know, at least in principle, which state I go to? So that's a paradox, and you can think and ponder about it. But let me just give you a hint. If you are trying to measure these things very, very precisely, you will discover that the location of this decay becomes less and less certain. So let's say that you measure the energy perfectly well, and then you are also trying to measure the momentum perfectly well. That will lead to the fact by uncertainty principle that you have no idea where in your pipe the decay takes place. And then after the position of your source becomes more and more uncertain, the phases of oscillations that come from different places would interfere destructively. And so in this limit, you get indeed no oscillation. But basically, the oscillations exist as a manifestation of the uncertainty principle. And if you talk to your colleagues who are doing quantum physics, you can say that, hey, I'm in neutrino physics. I have sort of a classic quantum phenomena with all the joys of quantum mechanics, paradoxes, and so forth. So the fact that you're producing a system in a superposition of 2 or more mass eigenstates means that this is only allowed because of the uncertainty principle. Okay. That's what I want to say about this for now, but we can come back to this later. Now, since we're doing quantum mechanics, let's do at least one more item for today, which is related to the quantumness, and that's the spin analogy. So if I have a 2-flavor system, it's basically an SU2 phenomenon, then any 2-flavor system can be thought of as a spin. So if I have a state, I can simply define the expectation value of this state. And this expectation value, the polarization of the spin, is the one way to describe the state of this 2-flavor system. So this, of course, it takes a 2-spinner and it maps it into a vector. It's a standard thing that you do when you go from spinners to vectors. But here we're just going to take this a bit more and see what that means. So I have a vector that I represent in this way. This vector is called the block vector. And it points somewhere on the sphere of possibilities. So it's called the block sphere. Did I lose my video again?
Yep.
Okay, sorry about this. Okay, yeah, so I take my spin state and I simply construct its expectation value, and I get this representation, graphical representation of the spin state, that it points somewhere on the sphere. And this is called the Bloch sphere, named after Felix Bloch, who had been thinking about this. Okay, I have to turn off some things that are happening here. Okay, my apologies. Just when things were starting to get interesting. So first of all, there is a one-to-one mapping, but second, we are interested to know how this object evolves. And to see how this object evolves, we simply differentiate its definition and apply the Schrodinger equation. So you get this. And then, of course, what we know is that here we simply apply the Schrodinger equation. So we get the state times the Hamiltonian with an I here. And here we get the same thing with a minus I. And then I can collect things into what looks like a commutator between the spins and the Hamiltonian. And now I have to look at my Hamiltonian. So the Hamiltonian that has a form that I've already sort of alluded at, but let me write this explicitly, is delta cosine 2 theta, delta sine 2 theta, delta sine 2 theta, delta cosine 2 theta. This simply follows from the definition of the mass basis and the mixing angles. You take the mass basis Hamiltonian and you rotate it to the flavor basis. But what I would like to do here is I notice that it is a combination of the sigma 3 matrix. So these diagonal terms are giving me a sigma 3 matrix and then a sigma 1 matrix. Okay, so I just simply decomposed this as the sum of two Pauli matrices. Okay, Andrea has taken off. Okay. We should Alex another 10 minutes. Yeah, let's do that. Okay, so we have this decomposition, and basically what it means is that H can be also decomposed in this where the vector H is delta sine 2 theta, 0, and minus delta cosine. I just reshuffle things. So H, can you hear me? Hello?
Yeah,
Yes,
you're
we can
there.
hear you.
No problem.
Okay, sorry. The Zoom says that there is that my connection froze. Okay, never mind. So then for the purpose of this thing, I just plug this H into the commutator, and I'm actually almost done, and I have some interesting result. So I get Hj sigma I sigma j psi, and I know what this commutator is extremely well, and it's 2 epsilon I j k sigma k. Okay, so I have Hj 2 epsilon k times, again, my definition of P, right? So this is Pk, but then with the epsilon, what I have is a cross product. So what I found can just be written as a cross product of the vector H and the vectors P. Let's be a bit neater here. H and P. So what did I find? What I find in this picture is that I simply have a precession around some vector. So let's draw the block sphere again. So my H vector, which represents my vacuum oscillation Hamiltonian graphically, has two components. It has the Z component that's given by minus delta cosine 2 theta. So this angle is 2 theta. And then the X component, which is given by the corresponding thing with the cosine replaced by the sine. And if I start in the state, which this way I have nu E, and this way I have nu mu, these are my basis states, then the evolution is a precession like that. So in terms of my oscillation physics, the same things that we've seen before actually look this way. I take a new E vector and it goes around in this space in a regular cone. So let's see if I can draw this. So I have a cone, and then my initial state just goes around like this. The projection on the z-axis of the spin is nothing but the expression that we derived in terms of survival and disappearance probabilities. So this is if you want, this is the qubit that describes this two-state system. And that's what vacuum oscillations do. You prepare a two-state quantum system. You have the Hamiltonian that's misaligned with this system, denoted by the vector H. And then the quantum evolution is described by classical spin precession. I think for today, I should stop. I had more planned, but sorry, with my connections here, connection problems, it's been a bit difficult. But I also, really welcome questions that you guys have. I hope that if there is one thing that I managed to convince you of, is that we have, in case of neutrino masses, we have an honest to God oscillation phenomenon that it has been observed in a number of cases, and that the three mixing angles, well, okay, I didn't argue how all the mixing angles have been measured, but theta 1,3 was measured by simply observing the oscillation wave in its classical sense. I want to show this now. And this was my level diagram for normal hierarchy and inverted hierarchy. The colored bands correspond to the flavor composition. And you have the solar and the atmospheric splittings that I alluded to before. So this is just to guide the eye. And now for atmospheric neutrinos, we also observe an oscillation pattern. It may not be as clear because their energy resolution is not as spectacular, but you can clearly see that for example, in this function, in this panel, as a function of the mixing angle of the zenith angle, things that go from the top that travel about 10 kilometers do not oscillate. Things that go through the Earth oscillate fully. And then as you go close to the horizon, you have a transition from full oscillation to complete non-oscillation as you change your baseline. And these things are also present in different energy bands. So this is the multi-GeV sample. And here, when you have sub-GeV sample here, the sub-GeV sample where you have a very low energy, then things oscillate from all directions, including from the top. So, oscillations are observed. This one is controlled by the 2-3 mixing angle. And so this was the one that won the Nobel Prize for superconductivity. Let's look here. This is the last illustration I want to make. Remember, I told you that the Camland detector is located about 150 kilometers from its source. And in this case, the solar mass splitting is at play, and the solar mixing angle is at play. You can see the unoscillated predicted spectrum here. And you can see, even by eye, right, that there are two clear dips. So there is a dip here, and there is a dip here. So this corresponds to the oscillation probability as a function of energy. And people have recast this data also as a function of L over E, and they also see expected oscillation behavior. So much for oscillations in simple cases. The next topic will be explaining the solar neutrino problem, and that will happen on Thursday. So is it correct to interpret the block diagram to mean it's always more likely to measure the neutrino in its nu e compared to nu mu? Very good. Very good. So in this case, for the diagram that I drew, it is indeed you're always more likely to measure neutrino as nu e greater than nu mu. Of course, the result depends on what the value of the mixing angle, I assume. So let me take a mixing angle equals to 45 degrees, which is called maximal. Then the 2 pi that 2 theta that I had before tells me that h is actually now pointing in this direction. And then my precession goes like this. Does that make sense? So I take this vector and I tilt it until I have maximal mixing. Yup, thank you. Okay, very good. So in this case, you can graphically see that if your mixing is maximal, then you start with nu e, you make maximal oscillation where you convert to nu mu, and then you go back. In fact, you know, this is relevant for what the NOVA experiment is trying to do. So NOVA is creating muon neutrinos, and then one of the measurements that they do in the FAR detector in northern Minnesota is they look at the muon neutrinos that survive. They have some energy at which they expect the oscillation to be maximal, and then they measure how many neutrinos at that energy still arrive. And that's their way of determining the value of theta 23. I will show that on Thursday, exactly, you know, how that is manifested in their data. Okay. And incidentally, you can see here that for vacuum oscillations, if you go beyond pi over 4, then you again get a cone, and your survival probabilities are the same for angle theta and pi over 2 minus theta. This is true when you have vacuum oscillations. Once you add matter effect, it's no longer true. But for vacuum oscillations only, it's sufficient to consider the physical parameter space from 0 to pi over 4 in the mixing angle. Okay. Do we have any urgent questions? Okay, well, very, very good. What backgrounds do we expect in detecting neutrino signals? Well, many backgrounds, and that depends exactly on which experiment you're trying to do. So, of course, you know, it's an extremely relevant question for neutrino physics. First of all, that's why solar neutrinos are measured deep underground. Snow is a very deep setting, and even the home-stake setting is 48, 50 feet below ground. That's the reason why you go underground. Could you please give some references on the block diagram? Thanks. Okay, I will certainly think about what the good reference is. Block diagram will recur when we talk about other things like matter effects. So it's not the last time we're using it, I promise. Okay, are there any urgent questions? Then I thank you, everybody, for paying attention and for asking such good questions. And I'm happy to continue this at coffee in room E. Thanks very much.
All right, great. Thank you, Alex. So we'll pick up for a coffee break at 1 hour and 20 minutes.